Hello, everyone. Thanks for joining us today. Scott, would you like to do intros?
All right, very good. Hello, everyone. Thank you for joining. So I'm joined today by Greg Harmon and Nathan Schnittman. Greg and I founded the company a number of years ago. He's been leading the charge on the product, and Nathan has joined us recently and has been instrumental in setting our new path here. He is our COO and chief scientist. So thank you, Greg and Nathan.
Glad to be here.
All right, very good. So Jaxon has been working on this for a number of years, making AI trustworthy. And what does that really mean? We're going to drill right into that today. At the highest level, we are taking large language models, and we're focused predominantly on text-based use cases, large language models, and not adjusting the weights, not training them, not fine-tuning them, but verifying that they are aligned to specific use cases. So let me ask you, Nathan, how would you describe what the Jaxon Guardrails platform is all about?
So we have a number of different types of guardrails that we use to avoid the AI hallucination problem. AI, especially LLMs, is the ultimate in people pleasers. You ask it a question, it's giving you a probabilistic answer where it's doing its best to find the next word to fill in an answer. So if it doesn't know something, it's likely to make it up, and you end up with hallucinations. So we have multiple types of guardrails to help avoid the hallucination problem and give you assured and reliable use of your AI. The one that we're going to really dig on today is our Policy Rules Guardrail that gives some of the best reliability in terms of being able to use an LLM in critical situations where you really can't afford or really want to avoid mistakes.
Very good. Greg, I'm going to turn it over to you. And a similar question, what is it? But drill a little bit deeper into why we have built this platform and how does it address the so-called hallucination problem?
Yeah, well, the platform overall, as Nathan mentioned, can attack the issue of hallucinations and LLM-based errors in general in a number of different ways. But we're zooming in specifically on our policy rules and a technology we call DSAIL today. And the notion here is that while large language models and generative AI in general is really performing a good role these days as an integration layer between natural language in the case of LLMs or just the natural world, and what we can do with that, it's not so good at what computers are traditionally good at, which is rigorous logic, symbolic reasoning, and proofs more in the mathematical sense. But we still have some of the old technologies, symbolic logic and symbolic reasoning. And so one of the the approaches that's on a lot of folks' minds these days at the forefront of this technology of AI in general is neurosymbolic hybrids. How can we take this marvelous new way of interacting with the natural world, so to speak, with natural language, with the concepts that we live and think about, and still get some rigorous reasoning out of it? Now, drilling down a little more specifically into what we're doing, the basic idea is that you can't have your LLM generating the actual logic that you want to reason over if you also really need that logic to be robust and have a high level of assurance. However, you can create a neurosymbolic program that can address specific types of logic. It can answer certain questions. The challenge you then have is, and we've had with that technology, which has been around forever, is how do we get our original data when it's coming from complex documents, say, into the system so that we can reason about it, and that's where an LLM can shine. So really, what we're bringing to the table right now is a way to define particular particular robust problems in particular right now around policies and compliance, and then tie that back into complex original document, both for creating these the symbolic pieces of logic as well as when applying them to other pieces of document or just general information as it flows through.
All right, very good. I'm going to ask both of you this question also. Why now? What has come together so that it is possible to do what we're doing now? I'll go back to you, Nathan.
Well, it's a few different things. LLMs give us a great way to deal with unstructured data and represent it well and with reason over it. Provide those base pieces of information that we can then reason over. And the increased use of AI and LLMs in more and more parts of people's lives means the reliability, and so we saw that as a real need. Like, everyone's nervous that AI is out there doing certain things without some better idea that it's doing the right thing, not just doing something. And we've been doing a lot of work in sort of the government space where results really matter, and people aren't willing to take it on faith that they're getting the right answers. And so a bunch of our customers really pushed us to give them that assurance that they can use AI in a way that they're not making mistakes or operating on bad information.
All right, I'm going to ask you the same question, Greg, but I'm going to twist it a little bit because I think Nathan covered that pretty well. So everyone's running to this RAG technique, retrieval augmented generation. Can you explain how we add more rigor to that and what we mean by this graphic here?
Sure. I'm going to challenge the question a little bit. I'm not sure it's about adding rigor to RAG, but rather it's solving a slightly adjacent problem. So RAG is primarily a way that you can inject knowledge that the LLM didn't have during training into, whether it's because it was limited in terms of its corpus or because it's private information, into a context so that the LLM has facts available. So when it's looking for facts, the most common hallucinations will happen when it doesn't have an answer, and they have this real tendency to not be able to say, I don't know. So they'll find any answer that they can plug in, whatever seems like the most plausible of what's available. So you give it much higher, more plausible answers than it would have had naturally. But that doesn't give it the ability to do more complex reasoning. It simply provides it more facts that it can bring up. So the idea is that with or without RAG, you may have your facts, but you still at some point need to get into reasoning. And that, I think, if I can backtrack a little bit on the question, the way you'd asked Nathan, what's new now, what's different? I think it's the easy answer, I think, is, hey, LLMs are a thing now, and a few years ago they weren't. But I think to get a little more nuanced, LLMs are a thing, and they're starting to become good enough that much of the time they are really good at emulating reason. And we start to see the potential. We start to see, hey, we can apply them to these problems, but because of the opaque way in which they do it and the lack of guarantee, we can't quite get that last mile. And that's where we want to bridge over. We see the potential now, but it's so close, but not quite there when you need a certain level of assurance. And they have they sort of asymptotically approach that, but cannot actually bridge the gap, simply because they aren't built that way, and they aren't built to do that. They're probabilistic systems.
Very good. You said emulating reasoning, which I want to pin in and come right back to, but we have an audience question. How do you get from text to a proof a solver can process? I'm going to give a visual back here, and Nathan or Greg, you want to take this?
Yeah, I'd be happy to attach it. So the proof itself is effectively already templated by the guardrail and the symbolic reasoning we have underneath it. The real trick is, how do you get that? You have a program essentially, and that program has inputs, and then the question is, how do you get from, say, a big blob of text as an input to structured inputs that you can work with that program? And so what we're actually doing is we're actually moving the problem to something that language models can do pretty well, which is information extraction. So the idea is, for any input to a given program, you can break that down into data types, and you can imply questions. So I may not be able to ask one of the problems that we've been playing around with lately, back in the dev lab, is fair housing law compliance. So it's really difficult to take a big chat, say, between a prospective tenant and a landlord, and ask, does this violate fair housing law? But what's not difficult for an LLM to do is to look at that and to break it down into a small discrete question, something like, did the tenant or the landlord mention having a Section 8 voucher? It's a very simple yes/no question. It can be audited by humans in certain cases, but usually you don't need to. An LLM can answer that question with a pretty high degree of accuracy, because that's more of an info extraction. There's not a lot of reasoning that needs to be done. And from there, you can feed that tidbit of information into a more complex set of policy logic, along with several others that were extracted in a similar way. And that way you can seed what you need to evaluate your policies from the natural language, without having to make the full leap from info extraction all the way through reasoning, all within the course of a single prompt or LLM interaction, or even trying to get the heavier lifting done by the LLM. Let the LLM do what it does really well, and then have it step aside to actually put those different puzzle pieces together into the more complex question that you're trying to answer.
So, and I'd like to add to augment Greg's great explanation. We have a two-step process. There's an offline portion where you present the policy or regulations or documents or rules that you would like to have followed, that give you some of the bounds for the logic to operate over. And then there's an online portion where you're actually operating on inputs, whether that's emails or chat or other documents, that extract the information and can run those formal methods, in this case an SMT solver, over those pieces of extracted information based on that offline pre-generated rule set.
All right, I just showed these two graphics, which I'm going to ask you both to drill into a little bit more, but let me go back to this slide here. So we're seeing this as a common workflow with our customers at DoD and a number of the other industry customers, where there is an existing policy or a set of rules that the analysts are currently following. And now we have new chunks of information coming in, either as LLM output or extracted from a document that they're trying to analyze. I guess I'll point this back at you, Greg. Can you explain this workflow a little bit more as we think of it in a policy rules guardrail?
Yeah, and I think this is kind of what we've been circling around over the course of this conversation. But the policy documents, this is the bottom left, are really where the symbolic programs I've been talking about come from. So we aren't making up logic. We need to start from documents. These might be legal statutes. In the simple example I was referencing before, this would be fair housing law for the jurisdiction in question. From there, at configuration time, we'll use all of the goodness of LLMs and LLM code generation and so forth, with a domain-specific language that we've developed internally to express the parts of those policies that can pertain, in this case, to compliance rules. And we get that all set up so that then when it comes to inference time, in my example, this would be when we start actually monitoring chats between landlords and prospective tenants. That would be the data for review. We can run that through, do those lightweight data extraction problems I mentioned, and then let the DSL program process those inputs and give us back, analyses based on what the LLM was and wasn't able to, to bring out of the initial data. And I think one of the keys here as well is that you don't always have all the answers. So these programs and the stack on which we are executing a symbolic reasoning, it's based on the realm of SMT solvers and that ilk. And the idea is that you don't always have all the answers. You are not, every conversation between a tenant and a landlord is not going to touch on every corner of what's outlined as a possibility in fair housing law, which is pretty substantial. So the idea is based on what was present, can we either prove compliance or prove violation in some aspect, and then be able to do sort of attribution and breakdown back to this was compliant or this here was a violation, and here is the original part of the statute that makes us think that, because we're tracing back, and even these programs have this attribution back. And can we show that this is definitively the case? Many times we can't, and in that case we want to be able to say not enough information here, this is not provable. And again, this is exactly where asking an LLM to do the thing is going to fall down, because it's never going to say I don't know with a high degree of assurance. It's going to take the slightly more probable answer and just declare that as the truth, or overwhelm you with hedging and explanation, just depending on how the thing has been instruction tuned.
So Greg, I think that's a really great point that I want to foot stomp, right? Everybody's calling for explainable AI. One of the things that makes it kind of scary is you get an answer and you're not quite sure if it's right, you're not quite sure how it got it. Everyone's like, have faith in the process. One of the nice things about this rules approach is, we can tell you if there's been a violation or not, but with attribution. This is the information that led us to this conclusion, and you can go back and know why the answer was given, and look into pieces or modify the rules or make a decision knowing exactly what drove that output.
All right, very good. I'm going to call an audible here and go right into a demo to illustrate the point a little bit more. So in this particular application, here's the Jaxon platform where you create guardrails, but let me go a little bit deeper in here. What we're doing here is we're extracting rules from written policy. In this case, it's a policy around the workflow that an analyst would use for doing a background investigation on an individual. And the slice that I took in here is related to delinquent debt specifically. So we're copying and pasting or ingesting the document and pulling this natural language from it. From there, we are extracting the rules, and we are using LLMs for this step, so there is a propensity to hallucinate, but we have curbed it significantly with a whole bunch of prompt engineering and techniques that are getting utility LLMs, not the mainline LLM, but a utility LLM that we have instructed specifically on turning it into rules. These are editable, so a user can go in here and make changes willy-nilly. But the real goal here is to get it to the DSL, to get it to the domain-specific language that we're effectively creating a program with that has variables. And as new data comes in, we're extracting values for those variables, and that's what gets solved. Let me keep going here, and then I'll circle back to both you, Greg, and Nathan. So once we have the codified rules in this DSL, we can then generate questions from it. And this brings it back to natural language, where the subject matter experts that know the domain well, that know the questions that they typically would ask off the top of their head, or that they have in that policy document to begin with, are here. And these are also editable. You can click into any one of these and make edits as needed. They typically have been coming out really well and reflect the policy. And that's important because that's effectively what Greg and Nathan were just talking about around proving violation or compliance. These are the questions that we're asking the LLM. Effectively, all of the rules get married up into these questions that form a massive prompt that we're going to go back to the LLM and get answers from. And it's that question answer pair that we're evaluating and having the proof and all the goodness around symbolic reasoning to make things more deterministic.
So I want to jump in here real quick if I could. We've got a question from the audience, which I think this is starting to expose a little bit, but I want to address it directly. The question was, is what we're doing kind of like invariance over RDF triples to extract the Boolean formula for satisfiability? And the second part of that, yes, that's exactly what we're doing, is trying to express Booleans and get into satisfiability. That's precisely what we're doing in the back end. On the front end, we have looked into RDS. The trouble with going with RDS and triples is you get into the realm of ontology, which itself can be a heavy lift. For those who have been into that world, you're probably groaning inwardly a little bit. So these questions and answers and kind of what Scott was just showing is think of it as an approximation or a lightweight way to get at the same kind of effect without actually having to go to a full-on ontology. We find that we're able to get an awful lot of the mileage without the heft of a full-on triple store, and with these Q&A. There are cases, and we are looking at ways certainly to also make the more ontological and triple oriented approach be a little bit lighter weight. But we found that this is a great way to get a lot of mileage and be able to do a great deal of this with a very small amount of the effort. It's a nice kind of 80-20 type solution from that front.
And Scott, if you can go back a slide there, thanks, Greg, for that great answer to that question. I did want to add here that we can take in policies and regulations and things like that and generate these questions, and that's a great starting point. But there's also an opportunity here for individual organizations to augment and specify these questions to specifically address aspects that they care about, or add certain areas that are most important to them, or additional requirements that they might have above and beyond of something that's stored in a policy document. So there is an opportunity to do that and sort of really specialize what the system's doing to address a specific need of a company or a person. And then the difference between this and the next slide is where we go from offline to online, where you're actually, the rules have been generated and then we're going into implementing those rules, working on a specific piece of information. So please go ahead, Scott.
Right. So you have a policy that's been written, and the analysts are supposed to follow it. But we know that every analyst has their own special set of questions that they ask of the data. So how can we extract that and codify it? That's exactly what Nathan was just alluding to. Is you may not have everything from the get-go, but how can you build up that institutional knowledge in the form of these questions that will be reusable not only for that analyst, but across the organization. And if and when those analysts leaves, it stays with the organization. It's a very key point and value of this approach. All right, I was skipping ahead to this slide to also answer the question from the audience around the Boolean formula, is that you do in fact get a 0 or 1 dependent on the answer to the verification step for that specific rule. And all of the rules that you're throwing at it will come back in this yay or nay. You're looking at a test interface right now that we have in the platform. This would all be called upon via API and displayed in the app layer, however the app layer decides to display it.
And that's a great point, Scott. We have an API that could be called from someone else's dashboard if you were looking for something that could to integrate with flows you currently have. but we also have the ability to put our own app layer on top and provide a soup to nuts solution.
All right, I'm going to go back to a slide, just a couple of minutes left here. Please, any questions from the audience, this is a great time to ask them and we'll cover them. But I'm going to go back to slide 12 here and talk about runtime a little bit more. So Greg, let me put it back to you to explain what's happening here.
Yeah, so this is another viewpoint of what happens at inference time. So we've at this point, we've already processed our policy. We've already created our DSL program with the Boolean satisfiability logic baked into it. And we've already generated the questions that the LLM is going to ask of a particular chunk of input data that we want to process. So this is not fair housing law. This is the chat transcript between the tenant and the landlord that's being analyzed now. That data comes in, and the very first thing we're going to do is take those questions and let the LLM extract those answers. And those answers, again, are info extraction. They tend to be simple yes/no questions or value extraction, something like how much rent, how much monthly rent was being asked for that particular unit, or simple info extraction tasks like that. Depending on the level of assurance you have and the nature of the problem, there's an optional human review step. You can have a human jump into the workflow and review those answers. Again, anywhere there's an LLM, there is some possibility of that error being introduced by the LLM. So this is an opportunity to jump in there. Certainly not required, and the LLMs tend to be quite good at this sort of info extraction, but it is possible. With those answers, we have the input variables to that DSL logic, and at that point we can then run through. We're on the step 3 now. We can then actually evaluate it via the SMT solver, which allows us. You can think of this as evaluating true and false, but it's actually for folks who aren't familiar with SMT solvers, it's subtly different. It's actually satisfied or unsatisfied. So with the information at hand, can we prove certain assertions that are correct or not? And while those may roughly correspond with this thing is true or this thing is false, it tends to be more either this thing is provably true or there is a combination of the unknown variables, a scenario in which this could be provably true or there is not, and then how that gets interpreted in the context of the overall application is, well, it's part of the design of the problem. So in the particular example I've been using, we could either say that it is provably true that there's a violation, or else it's unclear, or we can flip it around and say we can provably show that the landlord's in compliance or not. And in this particular case, it tends to be a better fit to try to prove a violation. If you can't prove a violation, then legally, it's not there, right? In terms of the jeopardy, but you can flip that orientation of the satisfiability around depending on what the particular use case is.
Okay, very good. We have one last question from the audience. What LLMs can we use? And I'll cover this one. We have a really good relationship with IBM. We are silver partners, and we can access any of the Watson X models. But really, we work with any LLM, any open source LLM, any commercial LLM. We'll tie into any environment to be able to use those LLMs. We're relatively agnostic. When it comes to the utility LLMs that we're in control of, that's a little bit different answer, and those are specific to the task at hand. An extension to this question, it wasn't specifically asked, but let me answer it anyway. As far as deployments are concerned, we work a lot with the federal government where it has to work on premises in air-gapped environments, so no access to the internet. So working with open source LLMs have been a good flair for us, but we are completely agnostic in that regard. All right, very good. I think we are out of time. Thank you so much, Greg and Nathan. Great conversation. Let's do this more often.
Thanks a lot. Talk to you soon.
Thanks all.
All right.
Thanks for coming.
Bye now.